In this series of videos, we're going to continue to apply derivatives. And a difference in this series from the previous series is that here we have to come up with the model that we're going to use, and in the previous one we were usually given an equation. Here we've got a rectangle that's growing, and the length is increasing at a rate of 8 centimeters per second. The width is increasing at a rate of 3 centimeters per second. And then we're asked, how fast is the area of the rectangle increasing when the length is 20 centimeters and the width is 10 centimeters? And you might wonder, like, how does a rectangle ever grow in size? Well, here's one that's growing in size. Okay, let's pick apart this question here. How fast is the area of the rectangle increasing? Right away, using calculus, that means we want dA dt. And we know it's dt, well, we know it's a because we're talking about the area changing. And then dt, because our other rates are given in centimeters per second, and we're probably in this series of videos usually going to be looking at time. We are also asked how fast, and that's going to indicate time. So we want dA dt, which means we need an a in order to find dA dt, right? We're talking about the area of a rectangle. Area is length times width. Starting with area equals length times width, we are going to differentiate both sides with respect to time, because that's how I'm going to get dA dt. So I have d dt of a is equal to d dt of L times W. On the left-hand side, we have dA dt. On the right-hand side, I'm not sure why I'm writing in blue, but hey, I'm committed, so I'm going to keep going. On the right-hand side, we have d dt of L times W. Folks, this is going to bring to mind two things. Number one, we need a product rule. We are differentiating the product of L and W. Number two, what we're differentiating, L and W, are not the same variable as what we're differentiating with respect to, which is t. And so this should bring to mind an implicit differentiation. We're going to say u is equal to L and v is equal to W. Our derivatives are with respect to t, and so we're going to say that u prime is, I'm going to write it as dl dt. I guess I'll tell you why in just a minute. And then v prime is equal to dw dt. I'm thinking of it in those terms because in the statement of the problem, we have that the length of a rectangle is increasing at a rate of 8 centimeters per second. That 8 is dl dt. It's how the length is changing over time. And then we have the width increasing at a rate of 3 centimeters per second. That is a dw dt. Another reason, though, is that if I just wrote L prime and W prime, it might not emphasize to myself that everything is with respect to t. So you're going to keep seeing me using dt throughout this series of videos. Now, using the product rule, I have u prime v plus uv prime for the derivative. So our derivative is w dl dt plus L dw dt. Now you'll notice we have numbers to put in place of dl dt and dw dt. We also have numbers to put in place of L is 20, and W is 10. Substituting those numbers gives me that dA dt is equal to 10 times 8 plus 20 times 3, or dA dt is equal to 140. We were talking about an area increasing. The units were in centimeters, so we're looking at square centimeters per second. Or to use, I guess, good form here, the area of the rectangle is increasing at a rate of 140 square centimeters per second. Now I want to talk about the name of this series of videos, related rates. This derivative here indicates that the rate at which the area is changing is related to the rates at which the length and width are changing. So this is saying this derivative is related to these derivatives. That'll be a common theme in this series of videos.